This video is on covalent bond energies. So a bond energy is the energy needed to break a bond. The energy of covalent bonds varies with the environment. Therefore, we must use the averages. For example, if I were to look at a CH bond, if I look at methane, CH4, my hydrogens are all fairly close to my carbon because they're each sharing 2 electrons, one with itself and one with a carbon. As opposed to my length of my hydrogen bonds. Here, between my carbon and hydrogen, now my carbon is doubly paired to an oxygen, and that's going to change the distance between my hydrogen bonds. Because my hydrogen bonds have different energies, depending upon where they are, scientists have calculated the average bond energy based on different situations. So when we are looking at the average bond energies, or the bond energies needed to break and form bonds, we look at averages. So here we have table 8.4, the average bond energies listed in kilojoules per mole. We have single bonds on the left, multiple bonds on the right. Looking at single versus multiple bonds, single bonds are going to require less energy to break bonds than a multiple bond. Here we have a single carbon-carbon bond where we have one shared pair of electrons, and this is only going to take 347 kilojoules per mole to break the bond. As opposed to a double bond with 2 shared pairs of electrons, takes 614 kilojoules per mole to break, and a triple bond with 3 shared pairs of electrons take 839 kilojoules per mole. So the more electrons shared, the higher the energy it takes to break the bond. Also, these bonds get smaller. Bond length plays a role into the energy required to break a bond. As the number of bonds increases, the bond length decreases, so electrons are being shared across a smaller area. Here in table 8.5, we have a list of bond lengths for selected bonds. Mostly are bonds related with carbon. We can notice that our single, double to triple bonds for our carbon listed here, our single bond length is 154 picometers compared to a triple bond length of 120 picometers. We can also see that as the bond length decreases, my number of bonds increases, my bond energy also increases. This holds true for carbon with oxygen and carbon with nitrogen. We can use bond energies to estimate the energy change in a chemical reaction. A reaction, we remember, is rearranging atoms, where we must break bonds and form new bonds. In order to break a bond, energy must be added, thus giving us a positive value. Forming bonds releases energy, giving us a negative value. To calculate the change in energy in a reaction, we can use the formula that our change in energy in the reaction is equal to the sum of bonds broken, or the energy of those bonds broken, minus the sum of the energy of the bonds formed. Knowing this, let's take a look at an example problem. Here I have a chemical reaction where methane is reacted with chlorine and fluorine to make my carbon-fluorine-chlorine compound, hydrofluoric acid, and hydrochloric acid. One thing that's helpful when figuring out these problems is to write out the Lewis structures of our different compounds. Here in CH4, my methane, I have 1, 2, 3, 4 carbon-hydrogen bonds. In my chlorine, I have 1, 2 chlorine-chlorine bonds. My fluorine, I have 1, 2 fluorine-fluorine bonds. So my total number of bonds broken, 1, 2, 3, 4, 5, 6, 7, 8 bonds broken. I have 4 carbon-hydrogen bonds. I have 2 chlorine-chlorine bonds, and I have 2 fluorine-fluorine bonds. If I look at bonds made, I have a carbon-fluorine and a carbon-fluorine, so there's 2 there. I have 2 carbon-chlorines. I have 2 hydrogen-fluorines and 2 hydrogen-chlorines. So my total number of bonds formed, 1, 2, 3, 4, 5, 6, 7, 8. So 8 total bonds formed, 2 carbon-fluorines, 2 carbon-chlorines, 2 hydrogen fluorines, and 2 hydrogen chlorides. We can look back at our chart on table 8.4 to find out the energies associated with these bonds broken and formed. So looking at this chart, I see that my carbon-hydrogen bond has a value of 413, and I have 4 of them, so 4 times 413, which is 1,652 kilojoules. My chlorine-chlorine bond, which is here, has a value of 239, and I have 2 of them, which is 478 kilojoules. And then I have 2 fluorine-fluorine bonds, which have a value of 154, which is 308 kilojoules. So in total, my energy that needs to be added to break bonds is 2,438 kilojoules to break bonds. My bond formed, I do the same thing. I look at my chart. I have 2 carbon-fluorine bonds, which are here. So 2 times 485, which is 970 kilojoules. I have 2 carbon-chlorines, which is here. 2 times 339, which is 678 kilojoules. I have 2 hydrogen fluorines, which are here, 565, which is 1,130 kilojoules. And then I have 2 hydrogen chlorines, which are here, 427, which is 854 kilojoules. So adding those up, there is 3,632 kilojoules of energy released when bonds are formed. Now to find out my total amount of energy for my reaction, I take my bonds broken minus my bond formed and the sum of the energies. That's what this E is sum of. So my delta H, my reaction, bonds broken, which is up here, minus my bonds formed, the energy required, gives me negative 1,194 kilojoules, which is exothermic, right, because of this negative sign. And that was the energy required to do my reaction.